Okay, let's look at some applications of the basics that we just saw in our first video. So first thing I want to talk about is batteries. Okay, batteries in our imaginary world of science, they're perfect. They don't have any resistance or any time lag. They don't generate any heat. In the real world, that chemical reaction inside of a battery produces some heat, which we would read then, because remember a resistor generates heat, so we would read that or model that as a resistor. So as you can see right here, this is what our more advanced model of what a battery is. It's got an EMF source, and then it's got a resistor inside. So we hook up between terminal A and B, and we get what's called a terminal voltage. Let's see if you can use Kirchhoff's rules to write an expression for what this terminal voltage would be. So I'd like for you to apply Kirchhoff's rules to this little circuit and see if you can figure out what the voltage is between A and B. All right, so here I've drawn it for you. So I have the current going around I, and then I've colored the circuit. Here's our highest volt part, but not all of that gets out of the battery. So I have a lower voltage coming out here because this resistor inside chews up or consumes some of the voltage. And then the external resistance of the circuit consumes the rest. Then we're back to where we were. So EMF minus IR internal resistance minus IR external resistance equals 0. So the terminal voltage just from A to B going across would just be this part right here, EMF minus IR. Now that will also be equal to the current times the resistance of the external part of the circuit. Now if we take a look again at this equation, we can see that it's a linear equation. So if we plot terminal voltage, VAB or V terminal, versus the current and rearrange the equation, we will see that we'll get an intercept right here that is equal to the EMF of the battery. That's what we're supposed to get out of the battery in theory, but we don't. And then over here, the x-intercept has a physical meaning. It's the maximum current that you can possibly get out of this battery. And as the battery gets older, its internal resistance goes up and up and up, and so we get a bigger negative slope, and eventually the maximum current that comes out of the battery is less than the device needs that we have it plugged into, so we have to throw the battery away, or put it in a device that needs less maximum current, and it'll still work. So the slope is the negative of the internal resistance if you graph this. Let's talk about bulbs and their brightness in a little more detail. So first thing is a bulb is nothing more than a resistor. It's just a resistor that gets hot enough to glow. So Ohm's law gives us that the potential difference across the resistor divided by the current going through the resistor will tell us what the resistance of the resistor is. All right? So like a 60-watt bulb is not really always a 60-watt bulb. When it's in the package, it's a 0-watt bulb. So it has to be hooked up to a potential difference. So the bulbs that we get at the store that we plug into the sockets in the ceiling, those are supposed to be hooked up to 120 volts. So it's only a 60-watt bulb when we hook it up to 120 volts here. The only thing about that bulb that remains constant is its resistance. So calculate its resistance either with this equation or this equation to find out what that constant is when we put it in the circuit. So the brightness of the bulb will depend on the power, the rate at which it's converting electrical energy into light or heat energy. So P equals IV. Now if we rearrange it, we can see that R is over here, so the bigger the current for that resistor, the brighter the bulb, or the bigger the voltage for that resistor bulb will give us the most brightness or power. So I'd like for you to look at these two. Rank the brightness of these bulbs, A, B, C, and rank the brightness of these bulbs, A, B, C, and D. So I've colored the circuits here so you can take a look at them. This bulb right here gets the standard full voltage of this battery. These two batteries are hooked in parallel. They look to be hooked up in the same, so this would still be the same voltage because this is the high end and low end of the battery. This bulb would just run twice as long because it has twice as much batteries there to make it run. It wouldn't make it go brighter, but it would make it run longer, twice as long. Now, if we hook the batteries up in series, if we think of Kirchhoff's rule, we would have an EMF plus another EMF, and then it all has to be consumed by this bulb down here. So this bulb will be brighter because it has a larger potential difference than these other two. So the brightness of these would be C is brighter than A and B, which are the same. Now in this set, instead of thinking about volts, it's a little easier to think about it in terms of current. So in this combination circuit, we have a main line here. So D has to be the brightest because it has all the current. And then the current splits, but this has two bulbs in it, so it's going to have twice the resistance, therefore half of the current compared to the path with only one bulb in it. So I2 will be twice as big as I1, so bulb A will be brighter than B and C. So D is the brightest, A is next, and then B and C are the same, but they're... Now what happens to the brightness of the bulbs when we remove bulb A, or we remove bulb B, or we remove bulb D? All right, pause the video, see if you can figure that out, and then I'll show you the answer. So to help you analyze this and get it correct, because on the test they're going to ask you to justify your answer. So let's go through this justification process. Here's the original circuit. If these are all resistors of R, then the total resistance will be R 5/3 R. So these two add up to 2R. This 2R is in parallel with this 1R, which gives us 2/3 R, and then this we add to it and we get 3/3 plus 2/3 gives us 5/3 R. That's the total resistance of the entire circuit. That's going to give us a total current that goes through bulb D of 3V over 5R. And then that splits 2 to 1 ratio here. So this gets 2/5 V over R, and B and C get 1/5 V over R. Now, here's what I'd like for you to do, is when you're doing these change problems where something in the circuit changes, just redraw it quick. Redraw what it looks like when the change is made to help you understand what's going on. So if we take out bulb A, we get this new circuit. This new circuit is simply series, and it has an equivalent resistance of 3R. So the resistance has gone up, which means that bulb D is going to get less overall current. The total current now is 1/3 V over R. So bulb D gets dimmer, B and C get brighter because they now have more current than they had before, and all of them have the same brightness. If we remove bulb B, if we redraw it, this whole section in here goes away because we've taken this one out, and that's going to take out B and C. So what we're left with is series again. The overall resistance has gone up a little, 2R from 5/3 R. So D does get dimmer. And then A and B go out, B and C go out. And then A gets a little brighter. If you look at the overall current, it's a little bit more than what it had before. This is 0.4 VR, and this is 0.5 V over R. And if we take out bulb D, that kills the entire current, the main line, and so all of that disappears, and we're left with an infinite amount of resistance, and therefore no current through anything. So they all go out. Okay, now let's apply Kirchhoff's rules to another circuit. In this particular case, I'd like for you to rank the currents through the ammeters. I have ammeter 1, 2, 3, and 4. And then to rank the potential differences across the resistors, I have 1, 2, 3, 4 resistors right here. Okay, pause the video, work that one out, and then we'll do it together. Make sure you pause the video. All right, if we color the circuit to kind of help us visualize and draw our arrows for the current, we see that we have a main line current coming all the way around here, and call that current number 1 to match up ammeter 1. And then it splits into current 3 and current 4 going through ammeter 3 and 4. Current 3 splits into current 2 and current 5, at least that's what I numbered them, and then they recombine over here. So this little section right here is going to have the same current as this section here. And then it all combines back into the total. If we look at the voltage. We have a high voltage section here, an intermediate voltage section here, and the low voltage section here. All right, from this we can see that ammeter 1 is going to have the most current through it. That's the mainline current. And then it splits into two parts. Now, this current 3 is going to split into two pieces. Current 2, 5, and 4 all have to be the same because they have the same potential difference, red to yellow in my picture, and they all have the same resistance. So they all have the same current, but I3 is the combo of I2 and I5. So I3 is next, and then 2 and 4 are equal. Now for potential differences, this one obviously has the most current through the same resistance. Remember, delta V equals IR, so more current for the same resistance, more voltage. And then these three will have 1/3 of this current, so they'll have 1/3 of the volts each of this one. And so there we go, 1/3 each. When we have a switch in a circuit, I really want you to take the time to redraw the circuit, one with the switches open and one when the switch is closed, so you can analyze them separately so you don't get confused. So like in this particular picture right here, if you would look at the original with the switch open, this whole right side disappears and we're left with this circuit right here. When the switch is closed, well then it looks like this circuit here. So it helps you analyze what's going on if you just take a little time, waste a little paper, and draw the two circuits separately, and then you can analyze them separately to see what happens. Let's talk about short circuits. Short circuits are a connection that has, in theory, no resistance at all, or at least very little resistance, so that it is a bypass for a path of least resistance around something else. Now, a short circuit is not always a bad thing. You may want one. Like, for instance, in this case, we have a short circuit wire here, where when we close this, I've colored it so that it looks like the switch is closed, and it allows the potential to bypass and go to both sides of bulb B. So bulb B would go out. That may be your design goal. A short circuit is bad is when it provides a path of least resistance where the current will jump up too high and it will draw too much current, generate too much heat, and melt the wires and cause a fire. So that's our problem. So in this particular case, when the switch is open, then the current will go through both of the bulbs A and B. And when the switch is closed, I have a short circuit and bulb B drops out. Okay, now let's talk about capacitors. The rest of our video will talk about capacitors exclusively. So remember from static electricity, a capacitor is nothing more than two plates that are separated by an insulator. Technically, it's a disconnect in the circuit. It just has a lot of room for current to flow on to each of the plates. One plate will become positive charge, one plate will build up negative charge, and the charges on both plates will be exactly the same. Things to remember is that the equipotential lines between the plates are straight and they linearly decrease from the high volt to the low volt side, as you see in this picture. And that the electric field is uniform across from the positive plate to the negative plate, except around the edges. We can find the electric field of a capacitor by using this equation, delta V, the potential difference between the plates, and the distance between the plates. Remember, do not use the radial geometry equations for a parallel plate capacitor because it doesn't have radial geometry. Capacitance equals Q over V. Remember, capacitance is in farads. Q is in charge, in coulombs. Sorry, had a brain fart. And then delta V is the potential difference in volts. The charge on the plates is equal to C times delta V. To find the capacitance of a parallel plate capacitor, it's kappa, the insulator inside the plates. If they don't tell you what that is, assume it to be air or a vacuum, which is 1. And then epsilon naught is our constant, which we can look up on our constant sheet. And then A is the area of one capacitor plate, and D is the distance between the plates. The energy stored on the plates is equal to 1/2 Q delta V, or 1/2 CV squared. Let's apply Kirchhoff's rules to capacitors in a circuit. The current rule tells us that the current that passes through here all has to be accounted for. It doesn't disappear, right? Conservation of charge. So instead of current flow, think of it as charge flow. So the charge that flows off of this plate comes around through the battery and deposits on this plate, meaning that these two that are in series have to have the same charge always. So Q1 equals Q2 for capacitors in series. Now the voltage rule tells us that the electric potential across the capacitor has to add up to the total of the battery. So just like we did before, when we go around a loop, the volts that are added, or the EMF, here it's 200 volts. So we'd have a plus 200 volts, then we'd have a voltage drop across this capacitor and another voltage drop across this capacitor. And those two drops must add up to what was supplied. So EMF minus Q over C minus Q over C equals or should equal 0. And since they have to have the same Q, the Q can be factored out and we're left with 1 over C1 plus 1 over C2. This tells us that when we have capacitors in series, they add up as reciprocals. Now, this is the exact opposite of resistors. Okay, resistors in series just add up. Capacitors in series add as reciprocals. For capacitors in parallel, the voltage rule is probably where we should start. When we have a loop that goes around like this, Kirchhoff's loop rule says that the EMF that's added here has to all be consumed, or we have to have a voltage drop here that equals this one. So in this loop, we can see that this 4 microfarad capacitor has to be hooked up to 200 volts, and so does this one. They're in parallel. They have the exact same electric potential across them. Now, the current rule, or the charge rule, the charge that's flowing through the battery comes here. Some of it goes to the 4 microfarad capacitor. Some of it goes to the 2 microfarad capacitor. So the junction rule we had before, where current in equals current that comes out of a junction, tells us that the current that has passed through this battery must equal the current that is now deposited on these two total. So the charge that these two capacitors hold total must equal the charge of both of them added together. And since charge equals CV, so C1 delta V plus C2 delta V, the volts we already know are the same. So we can see that capacitors that are in parallel just add up. So again, this is the opposite of what we get with resistors. Okay, now let's talk about the time dependence of capacitors. Capacitors behave like a wire when they're uncharged. So when they don't have any charge on their plates, charge starts to flow onto this plate, there's plenty of room for them, and then that repels charge off the other plates. They behave as if current is flowing through them, even though it's not. They behave like a wire when they're uncharged. But once they get all filled up with charge, so this plate is all filled up with positive, this plate is all filled up with negative, so that the potential difference here equals the potential difference of what's pushing the charge on, then they can't hold any more charge. And so they behave as if they're an open switch because there's no more place for the charge to go. They act like a disconnect, which is what they are anyway. So whenever you have a capacitor in a circuit like this, what you need to do is, just like we did with switches, is redraw the circuit for what it looks like when it's uncharged and when it's charged. So like, here's our circuit right here. I have an open switch, and then I have a 15 ohm resistor and 10 ohm resistor and a 240 microfarad capacitor right here. When I close the switch, when this is uncharged, it's going to act like a wire. So to the electrons moving through here, it's going to look like this. So solve it like this at time equals 0. And then when time goes to infinity, or for a very long time, once this thing gets charged, this capacitor is going to act like an open switch. That's going to take this section of the circuit out. So this resistor disappears, And so our circuit goes from looking like this at time equals 0, uncharged, to like this when it's all charged up. Let's look at another example. In this one, I have a capacitor up here, and it's uncharged to begin with. I close the switch. What does it look like? Well, when it's uncharged, it acts like a wire. Look at that. That's no resistance. That's a short circuit, which means that current can flow all the way around here and completely bypass both of these internal resistors here. And so all we're left with is just this 2 ohm resistor hooked up to this 12 volt battery. That's it at the beginning. Now, once the capacitor is all charged, it acts like an open switch, which takes out the short circuit wire. So it disappears. And what I'm left with then is I have this 2 ohm resistor in the main line and these two up here in parallel. Look at one more. Here's one where the capacitor is put into the circuit by closing the switch. The switch doesn't keep current from flowing originally, though. So originally, current is flowing around like this through these 3 resistors. Then I close the switch. What happens? Well, when it's uncharged, it acts like a wire. So it's a short circuit wire. So this resistor disappears from the circuit, and the current through ammeter 1 goes to 0 when I close the switch. And then once the capacitor fills up, it's going to act like an open switch. So it's going to go back to behaving like it did at the beginning when this capacitor wasn't even in the circuit. Sometimes they'll hook up capacitors to bulbs and they'll ask about the brightness of the bulb. Same thing. So like here I have a bulb right here, and when it's originally working before the switch is closed, current is coming through here, through this resistor, through the bulb, through this resistor, and back around. So the bulb is on. I close the switch. I produce a short circuit wire if this is uncharged, so the bulb would go out. And then as the capacitor fills up, then this bulb gets brighter and brighter as more and more current goes through it, and the bulb goes back on. In this particular one, I close the switch, and this acts like a wire when it's uncharged. So originally, this bulb will light up. As soon as I close the switch, it lights up. And then as this fills up and becomes like an open switch, this bulb will eventually go out. All right, that's it. We have covered all the major ideas in circuits for AP Physics 2.